best part is like when he came up, oh sorry, and then you realize there's like 10 people that list, and so you're just like, yeah, it's too much work.
Oh yeah, yeah. All right.
Yes, number 22.
Number 22.
Yes.
Okay, number 22.
Yeah, that was confusing.
Yeah.
That sucked.
Woo!
Yeah.
Now,
I got like half.
again, at the beginning here, let's go through some of these ones. 22, 26, some of those. Again, it's important that as we go along, that we continue to compare what it is we're doing here with our derivatives with what we did in chapter 2, because we then need that in chapter 4 and so forth, so on. We want to continue to keep the concepts in mind and why we're doing derivatives, even though our focus is mostly for the gateway test next Tuesday, right?
Yes, sir.
Even more for some than others, but that is an important focus. And that is simply how do you do a derivative, right? So how do you find f prime? How do you find y prime? And f double prime, which of course would be the same thing, just do it twice, do it derivative again. By the way, on the gateway there won't be any second derivatives. You won't have to do it twice. Okay, so just f prime and y prime. So that's our emphasis. But we got to always remind ourselves why we're wanting to find f prime, y prime, right? Just like many times you remind yourself, why again am I taking this class? You sometimes have to stop and think about that. Remind yourself. Hopefully it's a good answer. But why are we doing this? Well, all the stuff in the chart. We want to do the derivative, set it equal to 0. Or the second derivative, set it equal to 0. Find stationary points. Those are also candidates for global maximum. All that stuff about functions. The things that we'll be doing when we get to chapter 4. So chapter 3 is just about, okay, now we know why we need derivatives, where we're going to use them, to talk about functions and their behavior. And so now we just need to spend some time making sure we can do derivatives of all the different functions we might encounter. Okay, so that's what we're doing. So these problems kind of mix in that chapter 2 stuff and those ideas, but will not be on the gateway. So 22 gives you this weird looking function here. It's got some stuff on the inside. Now, the chain rule that we learned yesterday is all about functions that are on the inside. We had a lot of people gone yesterday, so it'd be worth just mentioning this, that to understand the chain rule, you've got to be able to know what the inside of the function is versus the outside of the function. We're talking about this kind of thing. Some are very easy. And again, sorry for those people at home. See, there again, I did it again. Sine of x squared, it's very easy to see that x squared is on the inside of the sine function. But for e to the x squared, not quite as easy. So that's why I like to put parentheses there. They don't always in the book, but I think it's important. That is, the x squared there is on the inside of the e function. The e function is the outer function. So we're going to talk differently about those functions starting today when we do our derivative rules that we're going to be writing down here in a little bit. We won't talk about the e to the x function, but we'll just talk about the e function, or the sine function. Because knowing it's not always just sine of x, or e to the x. Usually it's got other stuff on the inside. Okay? A log, right? Base 3. This stuff here is the inside. That's pretty easy to tell. That's the inside. But what about 1 over x squared plus 3x? What's the inside of that function? The stuff on the bottom is actually the inside of that function, because what that function really is x squared plus 3x to the negative 1 power. So the x squared plus 3x is the inside stuff. Okay? That's most of the different functions we run into. Yes?
Okay, looking at how you know to the negative 1, you take the negative 1 now you don't drop the power.
Yes.
Yes, you do.
Yes, you do.
Okay, that's what I thought.
Yeah. And we'll look at one like that. But yes, if we were doing that derivative, that one we just wrote, we would bring the negative 1 down in front, drop the power to a negative 2. We would leave the inside alone, and we'd multiply by the derivative of the inside. That's the new thing from yesterday is we're not kicking out a 3, you know, or whatever the inside constant is. Now we've got messier stuff on the inside. What we do is we kick out the derivative of the inside. That's what we're doing. Okay, so that's the chain rule idea. All right, so anyway. So in 22, they ask for what? H prime of 1. Before we can find H prime of 1, we need
H prime of x.
Very good. We need H prime of x. There's H prime of x. Now before you start jotting that down, let's talk about this a minute. Chain rule says, when you have stuff on the inside, here's how you do it. You do the derivative of the outer function. The outer function is f. So when I wrote this, it's hard to tell now because it's all up there already, but when I wrote it, I did it this way. I said the derivative of the outer function, which is f. What do you write? F prime. That's the derivative of the outer function. Step 2, we leave the inside alone. So g of x over x squared plus 1. We always leave the inside alone. Times, step 3, derivative of the inside. Derivative of the inside. Now, just looking at that, I can tell that the derivative of the inside is going to be a mess. So when I go to write this, I do derivative of the outside, f prime, leave the inside alone, times, I just put a great big set of parentheses, because I know that I'm going to now multiply by the derivative of the inside. It's going to be a big mess. I don't want to worry about having the parentheses there. And so I'm going to put them, and then I can focus on what I need to. So now I can just focus on the derivative of the inside.
Did I pause? Yep, it's right there. Left my water.
Oh, okay.
Sorry to interrupt.
That's all right. So now I'm looking at this thing on the inside. So I'm not looking at anything else but that. So what's the derivative of that? Well, what kind of rule do I need? The quotient rule, right? The u prime v minus uv prime all over v squared. So when I look at the inside and have to do the derivative of that, I look at it and say, hey, that's a quotient. That's a rule we learned 2 days ago. That's the quotient rule. So inside of here is going to go the quotient rule. So here's, and you can see, there it is. Quotient rule is derivative of the top, g prime, times the bottom left alone, has to be in parentheses, x squared plus 1, minus the top left alone, g, times the derivative of the bottom, which is 2x, all over the bottom squared. But that's just the chain rule. Derivative of the outside, leave the inside alone, multiply by the derivative of the inside, even though the derivative of the inside is fairly complex there. All right. Then they want h prime of 1. Well, that just means what? Plug in a 1. Everywhere you have an x. So everywhere I have an x, g of 1, 1 squared, g prime of 1, 1 squared, g of 1, 2 times 1, 1 squared. Let's put a 1 everywhere. And then I use all the information they gave me. G of 1 is 2. 1 squared plus 1 is 2. So this becomes f prime of 1. What's g prime of 1? That's 4. 1 squared plus 1 is 2. 4 times 2 is 8. G of 1 is 2. 2 times 2 is 4. So 8 minus 4 is 4. Down here I got 1 plus 1 is 2. 2 squared is 4. 4 over 4 is 1. So f prime of 1 is 7 times 1 is 7. Okay? These are usually like AP test, no calculator, multiple choice type questions. So you have your different options, and so you go through and you work it out like that. That would typically be a multiple choice type question. Usually it works out pretty nice. I mean, all those numbers were pretty easy to work, okay? As messy as it was. Okay, let's go to number 26. All right, 26 says g of x equals f of x squared. Again, you have a function on the inside. They ask us what? Now that's a different question than what we just did. That would, g prime of 0, we would put a 0 in for x. That's not what this one's asking. This is saying, first of all, do g prime, and then set it equal to 0. That's different than plug in a 0, whereas it's out but 0. So here's our derivative. Derivative of the outside to be f prime. We leave the x squared alone. We multiply by the derivative of the inside, derivative of 2x. Now, those of you who are gone especially, be sure and ask. I mean, that's fine. Go ahead and ask if you need to. The chain rule far and away is the most important rule, or the most common rule that we have, because almost always functions we do the derivative of have stuff on the inside. Okay? So we basically do it the way we've been doing it, where we kicked out a 3 or kicked out a 2. Well, now we're just saying what we're kicking out is a derivative of whatever's on the inside. So derivative of the outside, leave the inside alone. Kick out or multiply by the derivative of the inside. So there we go. So we need to know where that equals 0. Right? Where does g prime equal 0? Well, what you have are two things multiplied to equal 0. Now, this is important stuff here, right? Because this is a stationary point, isn't it? Where's g prime equal 0? That's like finding stationary point. So you have two things multiplied to equal 0. One of them's got to be 0. So either f prime of x squared equals 0 or 2x equals 0. Now, that's easy, right? That's just when x is 0. So there's one answer. Now this one's a little tricky. So you look in your book, they give you an f graph, right? Now this x squared is troublesome, so here's how I would approach it. Let's forget about that x squared a minute. Let's just do that. Because think about it, in chapter 1, we did this all the time. Where does f prime equal 0? We never said f prime of x. We would always say, where does f prime 0? When's f prime 0? When's g prime 0? So you look at the f graph, when is f prime 0? At 2. Now, when we were always asking when is f prime 0, it was f prime of x. So it was at x equals 2. But this is different. So what we really should be thinking is input and output. So what we should be looking at the f graph, when is its slope 0? When its input is 2. When its input is 2. So in other words, when that thing in there is 2. Now usually that thing in there is what? X, right? So it's when x is 2. But that thing in there is not an x this time. It's what? X squared. So what we need is we need the input to be 2. That's when f prime is 0. And so that's when x squared is 2. Which would be half right, plus or minus square root of 2. So there's three answers. When x is 0, or when x is root 2, or when x is negative root 2. Because either one of those, think about it, if you plug in root 2 for x right here, root 2 squared is 2, f prime of 2 is 0. You can see it right on the graph. Negative root 2 squared is root 2, or is 2, f prime of 2 is 0. It's a little bit different way of looking at it. You probably did some of that in Algebra 2 a little bit with composite functions. That's what's going on. Okay? There's going to be another one very similar to that when we get to 31. Okay, 27, same problem, same f, or same g, so same g prime. And what did they ask there? Is g increasing at -1, which is really asking, is g prime positive at -1? So we really need to find g prime of -1. So we plug a -1 in for x. -1 squared is 1. 2 times -1 is -2. What's f prime of 1? It's negative. That's all we really care about. Look at the f graph. The f graph's going down at 1, so f prime is negative. So this is clearly negative, and times -2, negative times negative, positive. So g prime at -1 is positive, so therefore g is increasing. Okay? So again, relating what we're doing back to the chart function. Stuff we could have done in chapter 2. The only problem is we didn't know how to do these derivatives in chapter 2. Now we do. All right. 31. They give you h as this generic function, and they also give you two graphs, an f and a g graph. And they ask for what? Stationary points of h, right? We need the stationary points of h, which is what? Where h prime equals 0. So we do h prime, which is just our chain rule, derivative of the outside, f prime, leave the inside alone, g of x, times derivative of the inside, g prime. Okay, that's just your generic chain rule right there. And so now this is very much like number 26. Where does this equal 0? You've got two things multiplied making 0. One of them has to be 0. So either f prime g of x is 0 or g prime of x is 0. we go to our that is exciting. We have that to look forward to. That's kind of spoiled. All right. So we are supposed to find out we have two things to look at. Where f prime of g of x is 0 and where g prime is 0. Those are the two things we're looking at. Let's do the second one first. It's easy. So where is g prime equal 0? There? Somewhere in there. I think in the back they call it 2.5. And it's kind of hard to see there. It's like multiple places. But we'll just call it that. Okay, so that's when x is negative 1.5 and 2.5. That's what we're looking for, values of x that will make h prime be 0. Well, we know that if g prime is 0, because of what we had when we solved it, if h prime is 0, that'll be one of the two things multiplied, it will make 0. So at negative 1.5, g prime is 0, and that. Okay, now we get to this one. This is very much like 26. Let's forget the g of x for a minute. This is asking when f prime is 0. When is f prime 0? Kind of looks like at 5 also. Now I think it turns out that doesn't end up being an answer, so if you left out the 5, you could be good. But it kind of looks like, usually at the endpoints we don't worry about that, but let's just put it in. But that's when the input to f prime is either 0 or 2 or 5, right? When in there is a 0, a 2, or a 5, f prime is 0, the input to f prime. But what is the input to f prime? G of x. So what we're really trying to find out is when does g of x equal 0? When is this input in here 0? Or when is g of x equal 2? Or when does g of x equal 5, right? So all of a sudden now they're outputs. They were inputs, now they're outputs. Well, that's what composition of functions are. You got the g function, you find its output, and then that's the input to the f prime. And so it's not surprising that's what happened. Okay, so we're looking at the f graph, we're seeing when its derivative is 0, and when that input into f prime is 0 in those three spots. So we want this input to be 0, 2, or 5. Well, this input is g of x. So when is g of x equal to 0, or 2, or 5? So here we go. When does g of x equal 0? 1, negative 4, and at 5. So when x equals negative 4, 1, or 5. So there's 3 more x values to make it work. What about when is g 2? 0 and negative 3 is when g is 2. So x equals 0 or negative 3. There's 2 more answers. When is g 5? Never. Not in that interval, for sure. So 1, 2, 3, 4, 5, 6, 7 different answers for stationary points of image. Okay? So, you think about what we did in chapter 2, find stationary points is very straightforward. Just do the derivative set equals 0, just an algebra solving thing. Well, this is if you have a table or if you have a graph. You know, same, you're still doing the same thing, but not necessarily algebraically defined. Okay? Still represents the same thing. All right, and I think that's all I have. So, do you have some that you want to look at? Some of those before those, right? Some of those that would be like the gateway test, like 15, 12, any of those. Okay? 15. Now, one of the things we said yesterday, so this would be for those of you that were gone especially, 15 would be kind of an interesting one. We talked about earlier today that we have to identify the outside function. What's the outer function here? The square. Because, and this is nice little short notation in trig class, but it really gets us in trouble in calculus. What cosine squared means is this. Cosine of x cubed That's what it means. We just put that little square there because it saves us a set of parentheses. It's just faster to write. But that's what it really means. So in calculus, when you see this, you ought to, and you can still write it, I don't care, but when you're working a problem, it's better to do this. Kind of like when you got a square root, it's better to put it to the 1/2 power. It's more useful. All right. So now the outer function is the square, right? So we're going to do the chain rule, and we're going to start by doing the derivative of the outside. So the outside function is the square. Now, here's something I mentioned to everybody yesterday. What I usually do in one like this is I'm doing the derivative of squared. Now, when we first learned derivative of squared, it was just bring down the 2, and it was just that. But it was only x. But now we're getting into things that aren't just x squared, just like we're getting into things that aren't just e to the x or ln x or sine x. We're getting other stuff on the inside. So when we write our rules today, I'm going to talk about that. I'm going to say we're not talking about the sine of x function anymore. We're talking about sine of some stuff. We're talking about e raised to some stuff. We're talking about some stuff squared. The stuff is like a group of x's. Okay, that's what we got. So what we're doing is, so when I write this, what I'll do is this. Now, this one it wouldn't have mattered, but I'll go ahead and do this and write that power there. Now, since it's a 1, I probably wouldn't have, but any other power would have. Because what I see people doing is they bring down that 2, and then they get so busy writing the inside, especially if it's messy, they get so busy writing the inside that after they get in writing it, they forget to drop the power. They just leave the power off. I can't tell you how many times I've done that. Like on the gateway, we got something to the 9th. They bring down the 9, they write all their stuff out, and then they do this. And then they go on to the derivative inside, and they forget that 8. And that's wrong. Just forgetting that 8, it's wrong. Okay? So what I usually do is when I have a problem like this, I'll go 9, parentheses, 8, and then I'll come back and write the inside. Just so I don't forget. All right. So now, derivative of the outside, got it. Leave the inside alone. Step 2. Right.
Is that 1 if they're necessary?
It is not necessary. And I usually do not write. Okay? So it's 3 steps. Derivative of the outside, which we did by bringing down the power, dropping it by 1. Second step, leave the inside alone. Third step, multiply by the derivative of the inside. Now, that's the inside. What am I going to have to do when I do that derivative? I got an inside and outside again, right? I got an inside and outside again. So when I do this, big set of parentheses for the derivative of the inside. So I'm saying, okay, I did the outside, I left the inside alone. Now I'm ready to do the derivative of this, but I can see it's going to be messy. So big set of parentheses, and now I can just focus on this red thing. So okay, I got the derivative of cosine x cubed. Well, what's the derivative of the outside? So I'm doing my 3 steps again. Negative sine. Second step, leave the inside alone. Third step, multiply by the derivative of its inside, which is 3x squared. One of the things we were talking about yesterday is then how do you have to leave your answer? Well, there is something you should simplify here. I've got this. Now, you look at these parentheses. These parentheses aren't really necessary. Right? Because it's this thing times this thing, then it's times this thing, then it's times that thing. It's like I have 4 things multiplied. So when you have A times B times C times D, you can just rearrange them however you want. So I should take this 2 and rearrange it with that 3 because that can make 6. And I would bring the x squared around 2. And then I got cosine x cubed. Since it's first power, I don't need those parentheses. And whoop, negative. Or stick that on there too. And then sine x cubed. If I left as this, that would be wrong because you did not put the 2 and the 3 and the negative 1 together. That's obvious simplifying. Many times, though, once you get to this line, you're done. I mean, a lot of the problems you do, there aren't things that can combine. But in this case, the 2 times the 3 can. And the negative 1 to make negative 6, those should combine. Whether you put the x squared over here or over here, I don't really care about that. But those things you should. All right, another one. (12) f of x equals, now, before I ever write, when I see a square root, I'm thinking, I'm not going to write square root, I'm going to write what? 1/2. It's on the bottom. negative 1/2. So before I ever write this one down, I think it's a waste of time to even write it the way they wrote it. When I see that, I'm going to write it e to the negative 3x, and then the whole thing to the negative 1/2 power. You've got to write it like that, or you can't do the derivative. You can't have it on the bottom and try to just do its derivative. Now, you can try a quotient rule, but I hate the quotient rule if you don't need it. If you've got 1 over something, don't do the quotient rule. 1's just a constant. I mean, technically, it's a function of x, and you do the derivative at the top, it should be 0, but the quotient rule is kind of messy, and if you can avoid it, avoid it. It's better to do it this way, okay? You can do a quotient rule, but it's better, it has to be right. And most time when I see people do a quotient rule and like that, they don't do it right. Okay, so that's just kind of my point. All right, so f prime, outside, then we're at that. So when we talk about the power rule today, we're going to talk about, hey, we got some stuff raised to a power. So what do? You bring the power down in front, you leave the stuff alone, you drop the power by 1. Then multiply by the derivative of whatever the stuff is, the inside. Well, that's what we got. So again, I would bring the negative 1/2 down, leave myself big parentheses, and then I would drop the power by 1 just so I don't forget about it. Derivative of the outside. Leave the inside alone. Times derivative of the inside. So put a big set of parentheses, so now I can do the derivative of the inside. Derivative of the inside is here in red. It's a derivative of that. So it's a plus, so I just do each one separately. So 2x plus. Oh, now it's got its own inside, doesn't it? But it's an easy one. What do? We just kick out negative 3. We're not bringing down. It's not a power rule. We're not bringing down negative 3. What we're doing is kicking out the derivative of the inside. That's the inside of it. And we're just kicking out negative 3. We're so used to that, that's probably pretty easy. So negative 3e to the negative 3x. Plus minus, just put a minus there. That'd be good. Now, back to your question, whoever asked in a minute. Can we leave it like this? Huh? Can we leave it like that, or is there something we could simplify, some obvious simplifying? My definition of obvious. What's that? I'd have to distribute it. I mean, I could take this negative 1/2 and distribute it through here. Now, I couldn't distribute it here, right? Whenever you got parentheses with a power, you can't be distributing stuff into it, right? There's not much you can do with that when you got parentheses to a power. But this I could distribute here, would cancel that 2, but then they're just giving me a fraction, right? I mean, I like the idea that if this was a 2 and this was a 6, I distribute that half, it would reduce them to whole numbers. But I'd just be trading one fraction for another, and I don't think that's a big deal. If you did, it'd be okay. If you do extra stuff that's not necessary, that's fine. Just do it right. I mean, if this is part of your answer, x plus 4 squared, you just leave it. Unless foiling it helps some things to combine or cancel or something. But otherwise, you just leave it. But then if you went to a new step and did this, see, you're going to get that wrong, because that's not right. So it's really never wrong to do correct mathematics. It just might be unnecessary mathematics. Okay? But as soon as you do something incorrect, that's bad. So, people get scared to try anything because they're afraid that they'll do it wrong, but then sometimes you need to do something, so. Now, if you look this up in the back, they would do several things to it. Like they think of this over 1 and this over 1, and they make this negative power go to the bottom with that 2, so they'd have this negative 1 on top, then they'd have this stuff on top, negative 3e to the negative 3x, like this, and then they put this 2 on the bottom, and then they'd have this down on the bottom, and they might even do the 3 halves then as a square root cubed or something. None of that's necessary. If you check it in the back, that may be how the back writes it. But it's not necessary. Now, that will be necessary. We get into chapter 4, we want to know where the stationary points are, we want to set equal to 0. We might need to write it like this so we can solve. That might be necessary. But right now, we don't worry about that. This one, you pretty much just can leave like that. Yes, Tim.
So how picky were you yet on the gateway without?
Well, that's what I'm trying to teach you right now is what are the obvious simplifying things to look for, like combining things, and then what are the things that aren't necessary. So I'm trying to show you those things now. Now, you said how picky. I'm a lot pickier the first one, you're gonna get 30 out of 30. You're gonna earn it. You know what I mean? If you're on your 7th one, I might be a little more lenient on those things, right? Okay, because I don't want to be grading them forever. You know, I'll be a little more lenient. That first one, definitely these things we've talked about. Okay, but I'm trying to show you on these problems which ones. Hey, you better be able to do this, but this, you know.
What's the most amount someone's taken?
Oh, I don't remember. It's changed over the years. You know. No, nobody over 10.
Five?
Anybody that went past 6 or 7 and usually given a drop or something. You know what I mean?
At least they care enough to come back sometimes.
Well, I'm not even sure that's true. I mean, yeah, you're right. They did come back, but they didn't care enough to ever study in between. You know, that's the problem. They kept getting 3 out of 10 every time. Well, just hoping they'd get easier, you know. Yeah.
So if we decided to do the quotient rule, what would the totally simplified solution of that look like?
Well,
Or is that just
Let's
extreme?
do it.
yeah.
Let's do it.
Did you do it?
I tried doing that.
I would remind me at the end of the period. Remind me at the end of the period. It would look different. It would look different because you'd have some stuff over some stuff squared, and it would look different. And it'd be okay. I mean, if you did it correctly, it'd be okay. If you did it correctly, it'd be okay. All right. I'll tell you what. Let's. Anybody else have one they just really want to see? Yeah. No. Page 195. Any more on page 176? Okay. All right. Well, later if you think of it, say something. All right. Page 195. Turn to that. Now, for those of you that were gone yesterday and could get your computer to work, I talked about page 195. And if you look at page 195, it's just got a whole bunch of problems, and actually there's some on the back we could do on page 196. Then it gets into some that probably don't worry about so much, but page 195. Now later on, maybe tomorrow or something, I'll go back to those websites that I showed you earlier. You could do those. I mean, some people just like kind of going to the website and doing some stuff, whatever. But I think if you would do all the ones on page 195 between now and Tuesday, that's good practice right there. Now, by tomorrow, if you've got all 54 of those done already, want some more? Good God. You know, then you can go to the website, I suppose. But that's just pretty good practice. Now, one nice thing about the website is it gives you some problems, and then you can type in your answer, and it'll check, and it'll tell you if they're right and stuff. And so that's kind of nice. Where here you got to look them up in the back, or you got to put them into your calculator and see if they match, and that's always not always quite as right. So you can sit here and work on 195 all day long and be doing them wrong all day, and maybe not even know if you couldn't figure out your calculator or whatever, couldn't figure out the back. So there might be a reason to go to the website. But what was the one we were talking about, John?
Number
7 or 8? It was 8, wasn't it? Okay. 7 was interesting, but 8 was really interesting. Okay, so let's take a look at number 8. So we have, now on number 8, they say, well, look at number 7. Number 7 says W of U. And so they use U as the input variable. And that's fine. I mean, you go through this page, they'll use Z and T and X and theta. And I mean, it doesn't matter. You can have anything as your input variable. On the gateway, I'll just use X. And so when you're working these, you might just want to have X be your input variable all the time. Keep things simple, for now. Later on, we get in chapter 4, we'll talk about why it's important to understand different variables, what's your input, what's your output, and so forth. But right now, if you just want to call them X. But on 8, they do. So we'll just go f of X equals, and then we have X to the 2/3 plus ln X all over e to the X times cosine 4X. All right, so this one, so you're thinking about your rules, and what rule is this one? Two R's. What do you mean both? Okay, the bottom is a product. So there's a product rule in there, but first and foremost, it's quotient rule. So when you get to these problems, you have to think about that. Now, look at number 7 just for a minute. What is number 7? Oh, and by the way, number 8 also is a chain rule because there's an inside. Now it's easy inside, just 4x. We'll kick out a 4 there. So there's a chain rule. Okay, what about number 7? First and foremost, it's a product rule. But both of the pieces of the product have stuff on the inside. So you're going to be kicking out the derivative of the inside when you do those pieces, the u prime or the v prime. Okay, so you get these combination of the different rules that you have to do. So let's look at this one. So first and foremost, it's a quotient rule. So u prime v minus uv prime all over v squared, where your u is this one up here and your v is this one down here. Okay, so we start by doing what then? Derivative of the top. 2/3 to the negative 1/3 plus 1 over x. Okay? Then what? Multiply. I don't think so. I don't have anything that's a product yet, do I? I mean, this is not a product, right? So all I've done so far is u prime. Right? That's all I've done so far is u prime. Derivative of the top. Oh, who said that? Team effort. Were you getting goosebumps? A little bit. Right? Yeah. It was just something. It was something. It's different for everybody. Sometimes your ears burn. And almost, yeah, right. It affects, parentheses like that affect people differently, I know. But, yes, this absolutely has got to be in parentheses. Because it's all of that. It's the whole u prime times the v. And without that, we would not have been multiplying all of it. We'd only been multiplying the 1 over x. So that has to be in parentheses. All right, times v, which is all that. E to the x cosine 4x. Now, does that need to be in parentheses? No. Not really, because they're multiplied. When you have a sum, that's when, or a difference, that's when you really need those parentheses. Because what we have here is this quantity, call that a, times b, times c. A times b times c, I mean, they're just 3 things multiplied. So it's not really important to put the parentheses in. It would be okay to have them there, okay? But you really be preferable if you understand when you need parentheses and you're just not putting parentheses around stuff because, oh God, he said put parentheses around these things, so you start putting parentheses around it. I mean, that can be more confusing if you do that. All right, minus. So now, okay, so that took care of that. Minus. Now we're doing u left alone. Quantity, that's right. I should have just put parentheses right away. X to the 2/3 plus ln x times v prime. Now I changed to red, so that's got to mean something. It means danger, right? What's v prime? That's the derivative of the bottom. That's when I need the product rule. Because I'm now about to do the derivative of a product, I need the product rule. So this big set of parentheses right here is for the v prime part, and that needs to be the product rule. So within the quotient rule, we needed a product rule. So now all I'm looking at is this bottom and thinking product rule. So what's product rule say? Derivative of the first, e to the x, cosine 4x left alone, plus, because what I'm doing now is u prime v plus uv prime, plus e to the x left alone. So that's going to make this a negative, and I'll be kicking out a 4, so I might as well stick that in front. Sine 4x. So e to the x was left alone. Derivative of cosine is negative sine 4x, and a 4 kicked out, so I'll put the negative 4 in front. I got that. All over e to the x, cosine 4x, all that. So, borderline, easy, medium. No, that's a hard. Definitely.
That's a hard one.
That would be a hard one. Now, is there any, back to Tim's question, is there anything that can simplify? Probably somewhere. Often on the quotient rule, there's some distributing or something you could do on top that might cancel some terms, might factor out something that can cancel at the bottom, possibly. Now, it's hard for me to just say, hey, I expect you to do this. Again, I'm saying it's obvious simplifying my definition, and it's kind of a loose definition, so it's hard to know. I understand that. Okay? To me, there's not. Usually, if they're all just x's and x squareds and stuff, the simplifying is easier. If they're all just e to the x's or all just sine x's, it's easier to see. This is a whole mixture of things. It's pretty tough. There actually is something in there that can simplify. It's not the cosine 4x. It's the e to the x. Now, you need to think about something here. What you can, like if I have 3x squared minus 5x, what can I factor out of that? And then let's say I had an x cubed down here. I can factor an x. Why? Because x is a factor of this and it's a factor of that. It's a factor of the entire top. So that's what you cancel, are common factors. So whatever you have here has to be a factor of the whole top. Now what the top is really two things. Let's do it in blue. The top is really this, which are three things. This, this, and this. And then it's this thing, which is this and that. Now, excuse me. So e to the x and cosine 4x are definitely a factor of this blue thing, right? Are they a factor of this thing? E to the x is, because what could I do in this red part? I could factor out an e to the x there. So then I'd have this, e to the x, and that. So e to the x would be a factor of this, e to the x would be a factor of this, so I could pull an e to the x out of the whole top. And down on the bottom, I not only have an e to the x, I have two of them, right? So I could cancel one of them with an e to the x up there. I would not expect you to do that. That's a little beyond, I think, what I would call the obvious simplifying. If you do it, if you saw it, you do it correctly, feel good about yourself, but no bonus. Do it for the sheer enjoyment. The cosine 4x is not a factor up here because you could not factor cosine 4x out of that red thing to make it a factor of the whole time. So that's why you wouldn't do that. So, but that is the process that you sometimes have with the quotient rule, where you can do something with each of those two things that you subtracted. You can pull something out, cancel it with something on the bottom. So sometimes that does appear. That one would be pretty messy. So really, there's nothing you can do. You do that one and boom, you're done. Brittany, question.
Could you do either like 4 or 6? What kind of
You're talking about on that 195?
Yeah.
Okay. Who else had their hand? Somebody else have a question? Okay. Number 4 or 6?
Yeah, your book just, when I looked at the answer.
Do you have a preference? I like 6. Okay. Thank you. Number 6 says h of z. I'm going to change that to f of x just to keep things easy for right now. So that would be ln parentheses pi times sine of e to the x. Correct? All right? So the outer function is ln. Now, I forgot to rewrite our derivative rules. We'll do that here in a minute. But when we write our rules for ln, ln x is no longer, the derivative is not 1 over x. What it is ln of some stuff. Let's see. Peanut is 1 over peanut times times the derivative of peanut. Peanut prime. Whatever. Okay? Okay? It's the stuff. If you got stuff on it, says ln of some stuff is 1 over that stuff times the derivative of that stuff. So when we do this derivative, it's 1 over pi sine e to the x. Now, what we just did there was steps 1 and 2 together. We did derivative of the outside, which was the ln, that's the 1 over, and then we left the inside alone. Okay, so when we wrote the peanut, when we wrote that stuff down there, what we were doing was leaving the inside alone. Okay, that's what was happening right there. Times the last thing, which is derivative of the inside. Now, pi is just a number, so it put parentheses here, may or may not need them, but let's put them. So the pi is just a number hanging out in front, and then we do the derivative of that. Well, that's an outer and inner thing. That's a chain rule, right? So we do the derivative of the outer part, the sine, which is cosine. We leave the e to the x alone, times derivative of the inside, which is e to the x. So this whole red parenthesis was the derivative of the inside of the ln, but when we did the derivative of the inside of the ln, we had something that had its own inside, so we had to tack on the derivative of that when we did it. Now, since this is multiplied by this is multiplied by this, we can just leave those all together. The parentheses are not needed. But there is one thing we could simplify. We can cancel the pi's, because this is like a 1. So what they do is they put this on top, cosine e to the x times e to the x over pi sine e to the x. Pi's cancel. This would be fine. I think in the answer book they wrote that as cotangent. Well, is it cosine e to the x over sine e to the x? Cotangent e to the x, right? So you could write it cotangent e to the x, cotangent of e to the x times e to the x, but wouldn't have to. This is fine. But the pi's canceling you should do. Okay? That's the difference. And that question comes up every year. Thank you very much. When I'm doing 3x squared plus 4, when I do the derivative of this, do I make that 3 a 0? No, it stays there, hangs out, bring the 2 down, you got 6x. However, when I do the derivative of 4 sitting there by itself, that is 0. Does that help? Yes. And it comes up all the time. You're right. When we have the pi there, it's just a constant. It just sits. I mean, unless I wanted to do a product rule with the pi and that, but again, that making it. No, whoa, whoa, whoa. If what was squared? If that whole thing was squared. Oh, then we'd have a whole nother thing, because then ln would be squared inside those. Then you bring the 2 down, then you'd have all that, the first. But you'd still end up doing this, and so the pi would still be right. Yes?
Okay, so I'm kind of confused. Back on where you said f prime, you kicked out the inside there. Why
Right.
didn't you use the product rule since it's pi times sine?
Because pi is a number. If I have 3x squared, and I want to do that derivative, technically that is a product, right? So we've never done the product rule before. Could I do the product? Matt was mentioning this to me yesterday at the end of the class. He said, well, 3 technically is a function of x, right? It's just a constant function. It is. So let's do the product rule of that. So the product rule of that, we would say, okay, derivative of the 3 is 0. We'd leave the x squared alone, plus 3 left alone. And what's the derivative of x squared? 2x. So that's 0. That's 6x. So then it becomes like, well, why do it that way, right? And so we could have done the same thing with the pi, which is just a number. But
So you don't have to do it when it's an actual.
when it's just a constant. And that was a rule we had actually for several days now. If you have a constant times a function, the constant just hangs out there while you do this. Yep. Yeah, it's fine.
So if it's both the chain rule and like I'm curious as to why there's not the quantity within the algorithm, the natural log. Why there's not
No, that is the chain rule. The peanut prime is the chain rule. That is a chain rule. Yeah, good question. This is a derivative of ln, the 1 over. And then the peanut prime is the chain rule. So on our rules, we're just going to throw the chain rule in all the time, just with the assumption that anytime we do the derivative of sine or e to the x or e to whatever, that it's sine of stuff. Now, if we get lucky and it's just sine of x, fine. Hey, but matter of fact, look at this. Sine of x. This, again, this is a conversation Matt and I had yesterday. Is that a chain rule problem?
Yeah.
Technically, yes. Isn't there an inside?
Yeah.
There always is an inside to a function. So technically, this is chain rule. Derivative of the outside is cosine. Leave the inside alone. Times the derivative of the inside. What's the derivative of x? Right? I mean, so technically, every function is a chain rule. You always tack on the derivative of the inside. It's just that a lot of times the derivative of the inside is 1. Matter of fact, that goes back to when we were doing this. ln3 is just a number, right? Remember I said that over and over. ln3 is just a number, just a number, just a number. What's the derivative of the number? 0, right? And I said, don't call this 1 over 3, right? Well, it turns out that if you have the chain rule, you actually could do that. You could say, hey, this is a function. It's constant, but it's a function. So you could say, all right, this is a chain rule. What's the derivative of ln? 1 over the inside times, what's the derivative inside? Derivative of 3 is 0. 0. Cancel, but it's 0, right? So, I mean, technically, you could think of that with even those simplest ones. They're just kind of special cases of the idea of the chain rule. Okay? All right.
Do we have time for one more? Really? This is what execution.
Which one?
For, Sam and I are talking about it, and we both have something
This is time well spent.
Yeah.
4 is f of x. I'm going to use that instead of the u there. But it would be x over 1 plus x squared to the... Now this one I would say is kind of 50-50 whether you should bring that up top as a negative power do product rule, right? Because you'd have x times this 1/2 quantity, do product rule, or leave it like this and do quotient rule. Was that your dilemma? Did you both do it 2 different ways?
We both just took it up. No.
You both took it up, okay? So you both wrote it this way. I think it's 50-50 on whether you should just leave it and do quotient rule or whether this would be negative now, right? The thing I like about doing quotient rule on this one is when you do the bottom squared, it would just get rid of that square root. So it automatically kind of makes that a little simpler. So that's why I might have been tempted to do that. But this would work. So let's do it as a product. So product says derivative of the first times 1 plus x squared to the negative 1/2 left alone plus x left alone, and then here we would bring down the negative 1/2. We would have 1 plus x squared to the negative 3/2 times the derivative of its inside, 2x. And it's not all over, right, because it's just product rule, right? So there's nothing underneath because we did product rule. So I can't really do anything with this. But over here, negative 1/2 times 2 is negative 1, right? And x times x is, so I should put those together. And then over here, I can't really do much of anything. And I would just leave it like that. Did that agree with either one of you? Brittany?
I know I messed up.
Now, if you chose quotient rule, it would definitely look different, right? I mean, we can just do it real quick. Derivative of the top is 1, bottom left alone. minus top left alone, derivative of the bottom. Pull down to 1/2, 1 plus x squared to the negative 1/2, kick out the derivative inside the 2x, right? All over that squared, which is just 1 plus x squared. And again, same thing, the 2 and the 1/2 would cancel. This x and this x would turn that into an x squared, right? And so it would be that. Which looks different than that, but they are the same, and you could just leave it. You could just leave this one. I wouldn't require you to do anything else. So, again, about 50-50 on which one is harder or easier. They're very, very simple. All right, stand up for 45 seconds, and we'll hit the stretch run here with a new thing we have to talk about. Yes. Yes.
So the black is
One x.
yeah.
Bring the 0 in front.
So it's actually
So that's which one is that? Hurry up.
So it'll be like.
All right, have a seat again. Have a seat, please. I know, but
Aren't you here to learn math, guy?
yeah, I'm on a roll. All right. See, that's where I wish I could pause the video. 45 seconds. All right. Now, don't take the time to write this down right now, because I will put this on the website. These are all the derivative rules, and we know them all now, but about 3, which we'll learn the last 3 tomorrow, and they're not too hard. Now, so I'm not going to give you enough time to write these all down right now. Many of them we've written. I'll put this on the website in PDF. You can print it off yourself. You can copy it down or whatever. I'll have it up other times where you can do that. I don't know. I'd rather not print them off for everybody, but because I'm not sure you need them. But they charge me for paper, and I use plain. But I mean, I could print them off. We'll see. But it's just kind of a summary of these different rules. I just want to explain the notation that you see here. Okay. Now, just look at the left column for a minute. So we've already went over these. Add, subtract, you just do their separate derivatives. You got a constant, you just keep the constant there. There's your product rule. There's your quotient rule. Okay, there's your chain rule, right? I mean, the ones that we've been doing here lately. So those are pretty obvious ones there. All right, now, the next one. The power rule. So this is how I want to think of the power rule. I don't want to think of it as x to the n power, because we don't usually have x to the n power. We usually have stuff raised to the half power, the third power, whatever. So the u just stands for a bunch of x's. The u just stands for a group of x's. Notice that I still call this derivative with respect to x, even though I'm using a u. Because what we're saying is the u is like a sine x, or an e to the x, or an x squared plus 7, or whatever. So the u just stands for some unknown group of x's, like peanut. Okay? All right. So the derivative is bring the power down in front, leave the u, the stuff alone, drop the power by 1, and then tack on the derivative of whatever the inside stuff is, the u prime. So what I've done is just build the chain rule into all the rules, because it usually is there. It usually is a part of it. And even like we said, even if it's sine x, the chain rule's kind of there. Derivative of the inside, derivative of x is 1. So, so that's how I've written the rules. So there's the power rule. There's e. E to some stuff is just e to that stuff times the derivative of the stuff. Based, I put a little asterisk by it because this is one when you're getting ready for the gateway test, you might want to just brush up on just a little bit that you remember, oh yeah, I got to tack on that ln, right? In other words, if I give you 3, I don't know if you had one of these in the homework ever yet, Okay, if you had 3, I was going to try to, no. 3 to the sine x, if you're going to do that derivative, it's 3 to some stuff. So it's 3 to that stuff left alone. What? Times ln 3 times cosine x. I mean, the ln 3 is there because it's part of the rule for 3 raised to some stuff. Okay, you got 3 to the sine x. You got to tack on the ln 3 because of the rule, and then you tack on the derivative of the inside. Okay, so that's what that rule is saying. All right. And then we got natural log, like we were saying earlier. It's just 1 over the stuff on the inside times the derivative of the inside. Log of another base, we got to tack on that 1 over ln 3. So again, that's another one you don't run into very often, so you kind of got to just refresh your memory on. So these are all rules we've had, just revisited now because of this chain rule thing we've learned about the derivative inside. Okay, sine, of course, the derivative of cosine. Cosine, the derivative is negative sine. Okay, now let me talk just a minute about these next two. These are the ones that were in your book. Yesterday we talked about them as quotient rule ones. We said, hey, take tangent, make it sine over cosine, do a quotient rule. Well, we don't really need to. We'll just memorize them. So those do need to be memorized. Derivative of tangent is secant squared. That's just what it is. And then, of course, times the derivative of the inside, whatever that would be. So derivative of tangent, secant squared. Just have to remember it. But if you remember that one, then cotangent's pretty easy. It's cosecant squared, but it's got a negative on it. The other thing you'll notice about the trig ones is all the co-functions are negative. Cosine is negative, cotangent is negative, and so is cosecant when we get to it here in a minute. So that's nice to remember that. So, and they're kind of paired up. Sine and cosine kind of pair together, tangent and cotangent kind of pair together, secant and cosecant kind of pair together. Okay, so if you remember derivative of tangent secant squared, pretty easy to remember cotangent is negative cosecant squared. All right, go back up to the top. I want you to see anything you're not supposed to, okay? Secant is secant tangent. You just have to remember that. When I say secant tangent, I mean secant of some stuff. The derivative is secant of that stuff times tangent of that stuff times whatever the derivative of the stuff is. And then cosecant's the same thing, except with a negative, it's cosecant and cotangent. So they kind of partner together. So if you memorize one, you pretty much memorize the other one pretty easy. And that is it. We've got these other three, these 3 inverse trig ones, which we'll talk about on Friday, and that's all the rules. You pretty much have everything you need. Learn those 3 rules, which work just the same as the rest of these. If you know them, it's just chain rule, and you know how to write them. So that's pretty easy. And so the last thing we have is this new thing we need to do today. Okay, and it's kind of out there. It's just different than all the other things we've done. I mean, it's still related. It's got chain rule in it, but it's the one you got to change your method of thinking a little bit. There won't be a ton of these on there, 1 or 2 at the most. But you don't want to mess these up, and then you got to get all the other harder ones and whatever that are there. Because the ones we're going to do right now, once you get the hang of it, is really not that hard. But in the beginning, it's going to seem weird. Other than just put it on the website?
Oh, website.
Okay.
My bad. I missed that.
Yeah. I am absolutely going to put it on the website. It might already be there. Files, it is not there. All right, we don't have time. All right, I'll get it up there. All right, this thing we're going to talk about right now is called implicit differentiation. This you probably want to write. Now, differentiation is the act of differentiating. That means doing the derivative. Differentiation is doing the derivative. Okay? All right, so what what is implicit differentiation? Well, as opposed to explicit differentiation. Well, okay, in mathematical sense, okay, mathematical sense, explicit means a function defined explicitly in terms of x, like this. Y equals, and then x. That's an explicit function. An implicit function would be one like this. X squared plus 2y squared equals 3y. Now that is not even a function, actually. It's like a tilted ellipse is what that would be. Okay? Now let's put a +4 at the end of that. That would be a tilted ellipse. So it's not even a function because it wouldn't pass the vertical line test, so it's a relation. But it does have slopes. It does have rates of change. And so it does have a y prime. Now it's really important that we talk about the input versus the output variable, the x versus the y. When we do these derivatives, we're doing the derivative with respect to x. So when we do y prime here, we're doing dy dx, the derivative of y with respect to x. Now we've never talked about this before because it hasn't been necessary, kind of like sine x was always cosine x, and we didn't talk about kicking out of 1 because it wasn't necessary at the time. But now that we know about chain rule, we can talk about it. Well, same thing here. When I tell you to do this derivative, you guys would always just write down a y prime right away. Right? If I tell you f of x, what's the derivative? You just wrote down f prime. But you know, when I do algebra with my little kiddos, my Algebra 1A kids, and we do this, you just look at that and tell it's 5. But what I have to tell them is, hey, you got to subtract 2 from both sides. Whatever you do to one side, you got to do the other side. You got to be fair. It's an equation. It's balanced. You got to do that. Okay? Well, technically, that's what we're doing here too. When we do the derivative here, we're doing the derivative of both sides with respect to x. On this side, what's the derivative with respect to x? 2x. Yeah, just your normal derivative. When you do the derivative to the input variable, it's just your normal derivative. But technically, what we've been doing is a derivative of this side too. What's the derivative of y with respect to x? Y prime. Now, you guys never thought of saying 1 there, right? You would just say y prime, right? But if I ask you what's the derivative of x, what would you say? 1. You wouldn't have said x prime, right? You would never thought to say x prime. If I said the derivative of x, you said 1. If I say the derivative of y, you say y prime. They're two different things. One's input, one's output. Well, this Leibniz notation helps us with that. If I do the derivative of y with respect to x, it's dy dx. If I do the derivative of x with respect to x, what's that? Dx dx. It's 1. Right? Dx over dx is just 1, right? So it makes sense. The derivative of x is just 1, because that's the input variable. Okay? So you could say x prime, I guess, but x prime is just 1, because it's a derivative with respect to x. So dx over dx, so it's just 1. So again, those seem like technicalities we didn't have to worry about before, but now we kind of do. Okay? And you'll see why here in a minute. So that was easy. We were done. Well, on this one, that's going to be more difficult, because number one, we can't write this explicitly. We can't get the y by itself. No matter how hard we try here, we cannot get the y by itself. But we still need to do the derivative. We still need to be able to find y prime in this problem. So how do we do it? Well, we do the derivative of both sides with respect to x. Okay? So let me write that one up here. So you could probably write that in your notes now. Now, when we first learned about derivative, we talked about f of x a lot. Now remember, f of x and y are the same thing, right? They're both the output. F of x and y are the same thing. The only reason we can't use f of x here is this isn't a function. It doesn't pass the vertical line test, so we can't use function notation for something that's not a function. But technically, f of x and y are the same thing. They represent the output. So when we do the derivative of f of x, it's f prime of x. When we do the derivative of y, it's y prime. Right? Okay. So what I'm going to do here is I'm going to do the derivative of both sides with respect to x. So what's the derivative of x squared? 2x. Right. Perfect. Just like normal. Plus. Now it's not normal. What's the derivative of 2y squared? It's kind of normal, but we have to do something a little bit special. Now, for some reason, if I write it this way, people don't have any problem. If I take out the y and I put f of x there, People seem to know what to do with this. So somehow my hope is you can transfer when it's written as f of x to when it's written as y. So tell me, if you were going to do the derivative of this, tell me what you would write. 4. Now I heard f prime, but why would it be f of x? Because it's leaving the inside alone, right? To the first. Doesn't it just feel like you have to tack on an f prime? Doesn't it? I mean, it's chain rule, right? So you bring the 2 down in front, which is 4. You leave the f of x alone, times the f prime. So now let's transfer that same thinking to that. What would it be? 4y. Isn't it? I mean, look. 4 f prime. 4y, y prime. Now, it's because of how we wrote it. When we wrote the f of x and put it in parentheses and squared it, it just felt like that was on the inside. And it was, so we had to bring the 2 down. Remember what y stands for. Y stands for some group of x's, like the u in our rules a minute ago. The y stands for some group of x's. It's just that it's an implicit function. It's implied to be a group of x's. We can't write the y equals, but y is some group of x's. So what I have here is not really 2y squared. I have 2 and then a group of x's squared. So when I bring that 2 down in front, I keep the group of x's alone. That's the y. And then I have to do the derivative of the group of x's. That's the y prime. Now, the long and short of it is this. Just remember it this way. I mean, I hope you would understand it and compare it to this, and that would all make sense. But in the end, it's basically this. When you get a problem that looks like this, it doesn't look like any of the other ones we've done, right? Because it's mixed up with x's and y's. So when you get one that's like this, you just remember this. The x ones, I just do the derivative like normal. The y ones, I do the derivative like normal, and then tack on a y prime. When I do a y derivative, do it like normal, tack on a y prime. It's really, that's all it is. So a normal derivative on this would be 4y, and then you would tack on a y prime. And that's really all you have to do. Well, I mean, there's more, but so what will the other side be? So 3y, normal derivative would just be 3, but we tack on a y prime. Derivative of 4, 0. Okay, now, so that's the first important step is to get that. Okay. After you get that, what's going to happen in these problems is you're going to have some terms, you're just going to have terms on each side. Some of the terms will have y prime on them and some won't. Remember what we're trying to get to. We're trying to get y prime equals. So now it's just an algebra equation. We've got to get the y prime by itself. Well, the way you get the y prime by itself is you group the y primes all together on one side. So we just need to move that over. So we got 3y prime minus 4y prime. So we just need to move that over. Then what? Factor out a y prime, which is 3 minus 4y. We just because that's every time that's going to happen. You're going to have some terms with y prime on because you tacked it on, and you're going to have some terms that don't have a y prime because it didn't have you didn't do a derivative of a y. So you didn't tack on a y prime. So all the terms that have y primes on them get on one side, get the other terms on the other side, factor out your y prime, and then what? Divide. And you got 2x over 3 minus 4y. And that's it. Now, it looks strange because you got x's and y's in your answer. And that's okay, because here's what they'll ask you then. You'll be done, usually. On the gateway, you'd be done. Now, in the homework, they might say, hey, now what's the slope of this ellipse at 1, negative 2? Put a 1 in for x, negative 2 in for y, and there. Implicit differential.
Wouldn't that be a differential equation then?
Yeah. What you end up with is technically a differential equation. It's an equation with derivative. Absolutely. Yep. Okay? Now, your homework is not very many problems. It's this. I don't have time to go through one all the way, but if I had, we probably have time to just do a little piece of it. Let's just say we have that right there. And even better, make that a minus. Okay? So, obviously this is now this one we could get the y by itself actually. We could factor out a y squared, we could move that over, we could square root both sides. Might even be worth doing one like that another day to show the two together. But right now we won't worry about it. So let's do the derivative of both sides. So what's the derivative of that?
6y.
Not plus, y prime. So 6y, y prime. I mean, once you get the hang of it, it's really not very hard. It's normal derivative tack on a y prime when you do the derivative of something with the y, because that's the output variable, not the input variable. That's why it's different. Now, this is tricky. What do you got here? Why is this tricky? This is a product rule. This is a product rule. Because, now I would take this negative and keep it stuck to the 2. I would treat this as a negative 2x times a y squared. That is a product rule, absolutely. So, most of you wouldn't have thought of that. Now you've seen it. I think you'll hopefully always think of it. You've got two functions of x. Remember, because y is just a group of x's. You've got two functions or two things multiplied together. So, derivative of the first. What's the derivative of negative 2x? Negative 2 times y squared left alone. Do we tack on a y prime? We didn't do the derivative of y, right? We just left it alone, so we don't tack on anything. Plus negative 2x left alone. See how by attaching that negative to that, I don't even have to worry about distributing or anything. It just comes along. Derivative of y squared? Whoop. 2y y prime. The derivative of y squared, normal derivative, would be 2y. Tack on the y prime. Now, don't leave that 2 there. Move it around with that 2 to make it 4. Okay? Equals, derivative of 7? 0. So now what do you got? You got a term there and a term there that have y primes in it. So keep those on one side. This would be minus 4xy y prime. Don't ever leave that 2 in the middle of a group of terms like that. This one that doesn't have a y prime on it, move it to the other side. Now take out your y prime. You got 6y minus 4xy equals 2y squared, and then final step, divide. Okay? It's called implicit differentiation. And there will be a few of these on the gateway. No more than 2. And they're just easy to tell because all the others will say y equals, and these will be a mixture of x and y. So here's your homework. The next line, 3.3, it's only a handful of problems are all these, but it's time to be getting on to page 195 and start going through those because you really know, unless it's an arc sine, arc cosine, or arc tangent, you know everything you need to know for the gateway test at this point. It's just about practicing that. That's on Tuesday. 3-4 is going to be tomorrow, which is basically I'm going to throw up the arc sine, arc cosine, and arc tangent rules. I'm going to talk a little bit about what the inverse string functions are. Not bad, it's got them. It's got them listed. And that derivative rule sheet that I post on the website, they're on that. And they are on the gateway too. So we'll talk about that a little bit tomorrow. Hopefully we'll have a lot of review time tomorrow, a lot of work time where you can work on problems just in groups or whatever, and I can work some for you and help you. And then Monday will be a lot of work time, a lot of practice time.
So,
Okay?
I have a question.
Yes.
Really quick. So whenever you have like because when you tacked on like